So I have an announcement to make. We at Moxie, we're starting a Kickstarter to get an app going. So this has been in the making for some time, or better said, we've put off making our own app, our own software for some time, hoping third parties would kind of get the job done and do it better than we could. But after many years, we decided that we need to, in order to really promote Moxie, we need to take on this project ourselves, and we're going to do it via Kickstarter. We're really excited about this. We think it's going to be really cool. Go take a look at the link. It's also in the comments section. You get to see that what we're looking at making is a smartphone app, a web tool, a cloud system to really maximize the Moxie as a tool. And we hope that you all want to come and support Moxie and get this done. And by supporting, you can look at the rewards. I definitely think it's worthwhile to support this. I think the value you're going to get is pretty high. And in order to bring home the point as to why Moxie is so important, that we need this app, is really to understand the importance of oxygen in not only things like performance diagnostics, but in general training all the time. And for all sports, not just endurance sports, but for interval or varied intensity, varied speed sports as well. So I was going to go through a contemporary view of bioenergetics and what NIRS reflects when you actually go into the field and use the tools. This is a classical view of bioenergetics, where you have the phosphagen system, ATP storage, you have the lactic acid, anaerobic system, and you have some aerobic system. Now this is somewhat outdated, and there's already alternative options that are available to you to explain bioenergetics. This is by Brooks and colleagues. It's a more contemporary model where you eliminate many of this, I would say, older terminology, where you get rid of terms like anaerobic and aerobic, and you go to something like oxidative, non-oxidative, where you make biochemical arguments as are oxygens present in the given pathway or not. So it gets much more to the direct point. And I would drive this home even further and 100% a contemporary bioenergy system that is in the end of it all oxygen driven, regardless of how you're producing energy. So first we'll talk about ATP storage, which we see in a classical model is something that's going to last a few seconds. You have ATP stored in your muscle, and this is obviously important to generate instant energy. Now the problem with ATP storage is that your ATP stores never actually deplete. Okay, so if we look at this image on the right here, you see that your ATP levels during a single contraction, we have a single contraction here, contraction and recovery in milliseconds at the bottom. You see that ATP actually flatlines. So ATP is never, you maintain ATP homeostasis throughout contractions, no matter how intense. So up efforts of 35, 65, 90% of VO2 max, your ATP hardly changes. Obviously ATP is being used, but if it doesn't change, it must be getting buffered somehow. And if ATP stores don't actually change, these 2 seconds previously talked about available to you has nothing really to do with your ATP storage per se, because that can't actually change. So the energy level has more to do with your ATP buffering capacities, or where you're getting your ATP from elsewhere, not the stores you have. So the first source of buffering is always this creatine phosphate, the high energy phosphates that you have available to you to buffer your ATP. And this is a system that is looked at as kind of like a 10-second system, classically. But already Brooks, in the model we looked at before, they talk even shorter terms. They're already talking 2 to 3 seconds of buffer capacity for creatine phosphate. So it's a very short-term buffer for very high intensity sports. That's what it's classically looked at. What we do see is that PCR does change drastically with contractions. So you have up to 90% of VO2 max. You have much larger changes in your PCR stores and your creatine phosphate stores than at 35% of VO2 max. And you see that in a single contraction, here on the right, that on the onset of contraction, your creatine phosphate goes down instantly, and you see your ATP again stays stable because it's getting buffered by this creatine phosphate. It's important to note here for later that you're within milliseconds of these contractions ending, you have recovery of your creatine phosphate levels. Now, this very quick buffering of creatine phosphate, of ATP via creatine phosphate, is very important because it lets you, it gives you very high energy flux. You get a lot of energy turnover very, very quickly, which you need for high intensity sports, high intensity exercises. The problem is that if we look at this decrease in creatine phosphate during a single contraction, within milliseconds, this is about 16 milliseconds, you have an over 10% drop in your creatine phosphate levels in one contraction. Okay, so if you kept doing these contractions, your creatine phosphate stores would be empty much quicker than what is stated as 5 to 10 seconds, even quicker than the 3 seconds mentioned in a more contemporary model. If you do the math yourself, if it's 10% in 16 milliseconds, in 160 milliseconds, you've emptied your creatine phosphate stores. Okay, which in terms of applied sports is instantaneous. Okay, so your ATP stores that are being buffered by creatine phosphate would be instantly empty upon any real time frame that is used in athletics. So creatine phosphate and ATP stores must somehow themselves also be getting buffered somewhere, or you must be getting ATP from somewhere else. You must be replenishing your creatine phosphate somewhere else. And so the next system that is often talked about then is your glycolysis system or glycogenolysis system. So the sugars that you have in your system and the sugars that are stored. This is then often termed the lactic acid system, the anaerobic system, because glycolysis itself, again, the non-oxidative system, doesn't use an oxygen in the glycolysis process itself. Okay, if you break it down to just that pathway, it doesn't use an oxygen. And it generates lactate as an end product, which we can get into later with the oxidative system. So that's why it's often called then the lactic acid system as well. The problem with this system is that if your glycolysis system is supposed to last, classically would be 400 meters is a classic glycolysis system, anaerobic system, bioenergetic event. So we're talking something in the realm of up to 60 seconds that it should be providing energy. So it should be providing ATP, it should be helping with your creatine phosphate for about 60 seconds. The problem here is that, as Schulin points out in this quote, if you have intramuscular glucose and glucose 6-phosphate less than 0.3 millimoles, which is a genuine estimation, you do not have nearly enough glucose around to maintain energy output for 60 seconds. Now, even let's say we go further than just intramuscular glucose, but you take your whole body circulating glucose. So you take a normal blood glucose level, and you take 5 liters of blood. Let's say you're looking at about 5 grams of glucose for your whole system in circulating blood, which is like 20 kilocalories. So you really don't actually have very much glucose available to you that should be maintaining this energy flux. So glycolysis in itself, as in the breakdown of glucose in your system, is likely not the contributor to generating this energy. So what we're left is then is we go from, well, not glycolysis, what about glycogenolysis? What about the stored sugars, not the circulating sugar that you have? And glycogen depletion is something that's often associated with fatigue. So this makes a lot of sense to consider this. And what's also, it's shown quite well, is that glycogen stays somewhat stable over short bouts of exercise. Okay, so this is a 30-minute exercise that I'm showing here. And after 30 minutes of exercise, you've lost some glycogen, but you still have glycogen available to you. This is also very training status dependent for multiple reasons. But glycogen depletion doesn't happen after 1 or 2 or 3 contractions or 1 or 2 or 3 minutes. Glycogen in your muscles is still available. But what's interesting to that point, it's a little bit like the ATP stores, is that if you approximate 1 millimole per gram of tissues of glycogen is being consumed to kind of refill your ATP, and your basic glycogen concentrations is 70 millimoles per gram, that you would actually have your glycogen stores depleted rather quickly as well. But that obviously doesn't happen, as we see on the right here. Your glycogen stores, which are now really driving your ATP supply, are somehow maintained. Okay. The question is, well, how are those being maintained? I mean, somewhere these glycogen stores that are being used up rather rapidly would be used up rather rapidly are actually being maintained. So how is this done? And this is where we get to the final system, when we get to the big cog behind it all. And this is cellular oxidation. It's the aerobic system. And the aerobic system is really the key that drives the entire bioenergetic system. So it's a set of cogs, as I've represented here. And you need to have this big cog running to have all the other cogs running. If you remove it, you're going to have a lot of problems. If you remove any of these cogs, you will, which we'll talk about later. Now all of a sudden, the most despised metabolic byproduct, lactate, for many years, now becomes the driver of this cellular oxidation and of this buffering of the entire ATP system. So what happens is, with this rapid rate of glycolysis and glycogenolysis to produce ATP, the end product is lactate. Well, it's pyruvate and or lactate. And now pyruvate under normal conditions would enter the mitochondria, and you would have cellular oxidation. But even because of LDH and the fact that LDH is so much more potent, you actually generate a lot more lactate than you do pyruvate. And lactate can also, in Brooks's lactate shuttle theory, enter directly into the mitochondria, where itself is then oxidized in the mitochondria. There's none of this going back to pyruvate thing. So it becomes a very direct and probably the most important glycogenetic precursor, because of its ability to be oxidized to help replenish glycogen stores. Now, it does this in different areas. So there's some evidence that it does this in glycolytic white tissue itself, that lactate can be used to replenish glycogen stores, which would explain why glycogenolysis can continue despite the high energy turnover, and why glycogen stores are maintained for a fairly long period of time during exercise. Further than that, outside of just glycolytic tissue, so white tissue, is that where you have the lactate shuttle happening within the cell itself, you also have intercellular lactate shuttle, or lactate shuttled around between glycolytic and oxidative, tissues. So, and that's what we see on the bottom right. And so what's happening is that this high rate of glycogenolysis and glycolysis is generating all this lactate, which is partially being used to replenish glycogen stores within the glycolytic fibers themselves. The rest of it is then through monocarboxylate transporters, your MCT1s and MCT4s, you're shuttling this lactate around, and it's this important gluconeogenic precursor. So it's used to continuously replenish glycogen stores, if that's in the glycolytic fibers themselves or elsewhere in the system, where lactate's being shuttled around and oxidized. And the lactate really then is the part of the cellular oxidation cog that links it directly to glycolysis, and why glycolysis and glycogenolysis and cellular oxidation can't really be separated from each other. They run together. Without cellular oxidation, your glycogenolysis system, your glycolysis, your glycolytic system doesn't really work. Furthermore than that is that creatine phosphate, which is this high energy buffer, is even more. They're all directly linked, but it's directly linked to cellular oxidation. And there's studies by Richardson that shows that creatine phosphate recovery, which we saw before, within milliseconds of every muscular contraction, this is dependent on oxygen availability. There's studies that show that. So your cellular oxidation is also directly buffering your creatine phosphate stores, to the point as why would muscle oxygenation measures be relevant for these high intensity sports is exactly for this reason, because creatine phosphate and the glycolytic system need cellular oxidation, need the oxidative system to maintain any kind of energy output longer than in a few seconds in applied terms. What is relevant though, and what is true, is that these different systems do have different rate or power when it comes to energy production. Okay, with the ATP and the creatine phosphate system being able to generate a lot more energy quickly than, let's say, the oxidative system. That's nonetheless true. And what this ends up doing in reality is that it generates a type of power duration curve. You see in the bottom here. So at the beginning of exercise, when you have creatine phosphate stores available to you, you can generate very quickly a high energy output. And you instantly, at the to buffer your creatine phosphate and then to buffer your glycolytic system, your cellular oxidation plays a role. Okay, but this takes some time to get going, and it doesn't have a very high, it's very efficient, but it doesn't have very high paced output of energy, which results in, once your creatine phosphate stores are used up, because again they drop, you're going to start having a drop in power, as we see with a classical power duration curve on the bottom right here. So there is consequences for having these three systems, but you need these three systems because they give you the ability to maintain exercise over a long period of time, but also to have these spikes here at the top. The relevant point is that for NIRS and from oxyuse is that the fact that cellular oxidation in the back turns all of this. It turns, if you're considering high energy phosphates, if that's the sport you're interested in, or if you're considering what would be termed anaerobic or glycolytic events, both of those are still directly linked to cellular oxidation, which we can see using NIRS. Now, it's going to be a little bit indirect, but it's certainly direct enough to get good feedback on it, which is all the studies that validate high energy phosphates and NIRS. There's a plethora of those studies available. Now, maybe to highlight the point a little bit about what happens if you want to take these systems apart and act as if they're separate systems. There's very good examples of that, and the one is McArdle's disease, which is a problem with phosphorylase. So they don't really run. So the glycolysis doesn't run for a person with McArdle's disease. So they eliminate the glycolytic system. And what happens is they don't produce any lactate, which you see on the bottom right here, which classically you would have thought would be a benefit if lactate was really so bad. But they actually have a huge decrease in performance. They have no performance output because the system here that's supposed to be intertwined, buffering each other, the glycolysis, the glycogenolysis that's supposed to be buffering your ATP storage when creatine phosphate's being used up, just isn't running. So the whole system slows down, which is what we see in McArdle's disease patients. Maybe a little bit longer than what I was hoping to make that. I was hoping to be short and concise, but I do think it's quite interesting. And if you have questions, please send that to me. And I hope it's clearer why a contemporary review of bioenergetics sets oxygen in the center point of not only endurance sports, which has always been like that with measures of VO2 and ideas of anaerobic, aerobic, but the fact that even in things classically considered anaerobic, oxygen still very much is in the center, and that all these energy systems that are non-oxidative, let's say, function on a time scale that is much, much, much shorter than what we thought. So it's much more in tune with anything over 5 seconds becomes highly oxidative, rather than this idea of post 60 seconds is oxidative. That seems to not be the case at all, which leads to discussions about oxygen debt and oxygen deficit and what those things even mean. Which is fair enough, because I think a lot of those terms are misused or misunderstood. And a lot of those terms have much more to do with the system at a global level and the time it takes for feedback loops to occur to get the oxygen transport system going, rather than what's actually happening in the muscle, which is highly aerobic, regardless of what kind of pulmonary ventilation debt or deficit that you think you're accumulating. Yeah, thank you very much. Go support the Kickstarter, please. If we could get this done, it would be pretty cool. I think everyone would enjoy, and then we could really get some cool features done for people to use. Thank you very much. Bye.